Welcome back to multivariate calculus. In this video, I want to talk about the radius of curvature for a curve. The idea of radius of curvature is the next way of analyzing and describing a curve beyond just simplifying it with a tangent line. Conceptually, it's a relatively straightforward idea, but analytically, it's actually going to take every tool that we have developed so far in our study of curves in space in order to make this work. Without further ado, let me get my head out of the way so I can start drawing a picture instead of trying to describe things entirely using words. So imagine a curve, probably a curve in space, but you can actually even think of this just as a curve in the plane, and that might make things a little bit simpler. Given any curve, there's always going to be a small enough window where in that window the curve is in a single plane. And so we can think about things just in those terms. Many times in your study of calculus, you've looked at a point on the curve and you have found another point infinitesimally close to that and drawn the line through those 2 points to call it the tangent line. Right. I'm going to define here the tangent line as a line through the point of interest and the next sequential point on the curve. Right? A line is a continuum of points. Talking about them in sequential order or the sequence of finding the one that comes next is nonsense. But if you stop and think about it, not really, because the whole structure of limits and the definition of the derivative is just a way of codifying an infinitesimally small step so you get to the next point without any other points being in between. So, okay, we can buy that the tangent line goes through 2 sequential points on the curve. I want to extend that idea by looking at not just 2 points, but 3 sequential points on the curve. Right? And this idea is going to give us what's called the osculating circle. Or you can think of it as the tangent circle. The terminology here is actually not that important because it's almost never referred to by name. But given 2 points, you no longer have a straight line. But it turns out that it is possible to find a circle which passes through any 3 points. And so we have a circle here which touches the curve in one place and 2 other places that are infinitesimally close to it. So we can define this osculating circle or this tangent circle as the circle through the point of interest and the next 2 sequential points. just like the tangent line is of practical use to us because it touches the curve at exactly one point, so too the oscillating circle is of practical use to us because it touches the curve at exactly one point. At that one point, the only way for that to happen is that the curve matches exactly the curve of the circle. And so that's why the thought of the oscillating circle or the tangent circle itself is not useful to us. The interesting thing is the radius of that circle. At this one point on the curve, how tight of a radius does the curve have? How small of a circle will it feel like we are spinning around if we follow along at this particular point? That's what we're looking for with radius of curvature. All right, so there's the visual of what we're going for. Calculation-wise, it turns out that this is completely backwards of how we should approach it. But this is the interesting thing, this is the visceral thing, so that's why I like to start with it anyway. Instead, we want to think about how fast does the curve bend away? So if we think about our arbitrary space curve, and we think about our point of interest on the curve, and we think about our tangent line, at the next point on the curve, there's a different tangent line. And so we can ask the question of how fast are we changing from one of these to the next? That's a nice way of thinking about. In a larger circle, our lines are relatively close together. In a tiny circle, to go the same amount of distance on the plane, suddenly our change is far greater. All right, so there's analytically what we're going to be looking at. In order to look at that, we need to think about the tangent vector. Tangent vector is given t of t is r prime of t divided by its magnitude. But it's not fair to see how this is changing with time. The thing that we need to keep constant is the step. How far do we go along the curve to get from one point to the next point? And we're trying to keep that consistent. So we need to take the derivative with respect to the arc length parameter of t hat. And of course, you saw in our previous discussion that we can take any curve and in theory, we can find the arc length function. We can solve for the unknown on that and we can use that and plug it in here to get the arc length parameterization. A really nice thing about the arc length parameterization that I asked you to look at in one of the problems to solve is that the magnitude of the derivative of the vector valued function under arc length parameterization is always 1. So if we are able to figure out the arc length parameterization, we are really just taking the derivative of r prime of s. All right, that's easy, right? I spent an entire video showing you that even though in theory this is a thing we can do, in a practical sense, it is generally impossible. So even though we would love this to work, it doesn't always work. And so we need to find a different way of approaching the situation. Thinking back to some of the things we've done with derivatives in the past, thankfully it is going to be possible for us. We've used the chain rule to very practical effect many times. But we can also use it when we don't know anything about the function. If we have a composition, f of u of x, we can think about that as f being a function of x, and we can expand out the chain rule. The derivative of f with respect to x is the derivative of f with respect to u evaluated at u of x multiplied by the derivative of u with respect to x. This is the f prime of u of x times u prime of x that you've used many times in the past, just written using the fraction notation for derivatives instead. And so curvature, which is generally denoted using the Greek letter kappa, which I have a hard time differentiating from my k's, but it is a kappa, not a k. Um, I differentiate it by using a curly line. I don't know if that's actually standard, but it works in my handwriting with the way that I write my letter K. Apparently, the way that I write my usual letter K in the English alphabet is a lot closer to what a kappa should look like. But um, as long as you get something that you can tell is different from your usual K, that's all we care about. We've defined that our curvature should be the derivative of t with respect to f. But if we're taking t as a function of s, remember what we really did there was we took t of s. And so we can use the chain rule to figure out how that should have worked. All right, so this should be the derivative of the tangent vector with respect to little t times the derivative of little t with respect to little s. But that's still not all that helpful. All right, this part is helpful. It's just t prime of t. This part is a little bit less helpful because if we had little t as a function of s in the first place, we wouldn't have anything to worry about here. But remember that t of s and s of t are inverse functions. And the derivative of f inverse of x is 1 over the derivative of f, evaluated at f inverse still, but 1 over the derivative. So dt ds that we have here is the reciprocal of ds dt. And that we know because s of t is the integral from 0 to t of the magnitude of r prime of tau d tau. And using the fundamental theorem of calculus, this means that s prime of t is r prime of t. I don't know about you, but I'm exhausted now. That used every scrap of everything we have talked about in calculus up until this point. But we got there. We no longer have to worry about the arc length parameterization, even though we know that that's where we came from. We found a way to get around it using everything that we knew. We had to rely on the fundamental theorem of calculus. We had to rely on the theorem for taking the derivative of an inverse function. We had to rely on definitions of all of these things. We have to rely on what arc length is. We have to rely on what the tangent vector is. Everything coming together in one place. Everything we have done with derivatives and integrals to get us to this point. But now we can calculate the curvature of a curve in space. To make sense of this, I'm going to start off with a very simple example. The curve r of t equals 3 cosine t, 3 sine of t is the curve that is a circle of radius 3. We know that a circle has a constant radius. So the curvature of this thing should be constant. But let's go ahead and calculate it anyway. All right. R prime of t is going to be negative 3 sine t, 3 cosine t. The magnitude is going to be the square root of 9 sine squared plus 9 cosine squared. Sine squared plus cosine squared is still 1, so we get the square root of 9, which is 3. T of t is going to be just divide those things. So 3 sine t divided by 3 is just sine t, and 3 cosine t divided by 3 is just cosine t. And finally, if we take the derivative here, right, the derivative may no longer be a unit vector, so I'm dropping the hat and putting a normal vector bar on top of it at that point. But the derivative of sine is cosine. Derivative of cosine is the negative of sine. And if you calculate the magnitude, of this, you'll get 1. So kappa is that 1 divided by that 3. If we call the radius of curvature capital R, we started out here looking for the radius of, or the curvature of a circle with radius 3. We got 1/3, which is exactly the reciprocal of the radius, and that's not a coincidence. In general, this value kappa is always going to be the reciprocal of the radius of the function. Here's one for you to try. Find the radius of curvature for the parametric curve given by the vector valued function r of t equals t 1/t. All right, this is a planar vector valued function, 2 dimensions, not 3 dimensions. That changes nothing about anything we've talked about. It just means that you have fewer components to deal with. You can probably think through and determine x component here is just t. That means that we could have written this as a Cartesian function if we wanted to, but I chose not to. So see what you can do with this. Find the radius of curvature for the parametric curve r of t has components t of 1/t when t is equal to 1, and I'll see you in the next video.